Okay, this next problem, we're uploading that last one. Little process I go through here. Okay, so this next problem, it kind of, riders in an amusement park, here, you all don't know how to do part A yet, unless you had, physics in high school. Unless you remember the potential energy is going to, at the top, is going to equal the kinetic energy at the bottom. That's a precursor. So this is a precursor for chapter 7 that we're going to start, on Tuesday, a week from Tuesday, right after the exam, after the exam and everything. But assuming they find the speed of the riders at the bottom of the arc. Well, it's kind of hard. It's kind of hard unless you unless you know about the potential. And so we'll here's a precursor into what's going to happen. So in this problem, what we have is this. What we have is this. But I like this problem because it forces us to look at what is the important component of this problem. So we've got this. It's kind of like that Viking. Well, in fact, I think they called it the Viking thing. So it's going to go from this height, and it's going to swing down, sweet chariot, down to here. I didn't draw this to scale very well. So it's going to go from, we're going to go from the bottom of this down to here. So that's going to be the height that it's going to go through as it swings down. And then it's going to have a speed here, a tangential speed. And this will be a linear or tangential speed at this point. Okay, and we have not talked about this. This will not be on the exam, but I just want to show you. And the way you do this is you take the mass of the gondola times gravity times h. mgh, that is called the gravitational, that's its potential energy. It's ready to do work. That's all potential energy means. It's something that can do work now. So we've got it up here, and then we're going to let it go. And then down at the bottom, it's going to be all kinetic energy. It's going to give up all this height which gives it its potential energy. It's going to use up its battery, and it's going to have nothing but velocity left, which is called the kinetic energy. And we just set those two things equal to each other. So you're getting like a little 3 to 4 minute lesson here. So we've got 1/2 mv squared is equal to mgh. I know that it's conserved because I don't think they gave me a mass of the thing. No, they did not. So I don't know the mass. But look, the masses cancel, and I get v squared is equal to 2gh. I multiply both sides by 2 here. And then v is equal to the square root of 2gh, which is a very fun, I mean, that little formula shows up all the time. It will not be on your upcoming test, though. It'll be on your next one, I guarantee it. It'll be on exam 3. It's going to be all over it. All right, so we got 2 times 9.8 times. Now, how high was it? 14 meters is the radius. H is equal to R. So it's 14 meters. So I just type it all in, square root times 14 is equal to 16.56 meters per second. Well, let's go with 16.6 meters per second. That's how fast it's going at the bottom. That's its tangential speed. Okay? Now, here's what's going on. The only thing that's working is this pendulum swinging back and forth, or this Viking thing is swinging back and forth. All right, so let's look at what happens to this little carrier at the bottom. All right? Let's take a look at what happens to a person sitting in this thing. We do it with jet pilots. We do it with all kinds of stuff. All right, so anyway, here we go. So we've got this person sitting in this little gondola, all right, on their seat. And so they've got a normal force. They've got mg. Okay, now what's the normal force that they feel? Well, they also have, as they're going like this, and they're going in a circular motion. Since this is a tangential or linear velocity of 16.6 meters per second, then they also have a centripetal acceleration. Their net acceleration is going this way, up. That's the key to this whole thing. They've got a net acceleration that is going up. They only have these two forces. So we got to calculate that normal force. Okay? And that net acceleration is 16.6 squared over over what the hell's the height of the damn thing? 14. Sorry. Over 14 meters. I kind of forgot myself there for a second. Sorry. I apologize. So we got 16.6 squared divided by 14. That is the acceleration. Is equal to 19.68 meters per second squared. That's like around 2 G's. But wait, what's the force that she feels? The person sitting in this car. The force that the person sitting in that car feels. So let's look at the sum of the forces in the y direction. Well, it does have a centripetal acceleration going up at that point, which is going to equal the normal force minus mg. Oh my gosh, that normal force is huge. It's going to equal MAC, which is the mass times this, plus mg. And if her mass is 60 kilograms, the mass of the rider is 60 kilograms, then the normal force then is equal to 60 times 19.68 plus 60 times 9.8. Now look at this. This is almost 2 G's, and there's another, so it's 3 G's. It's damn near 3 G's of force that she's pulling. Okay? Let's see if we're right. Well, let's calculate the numbers. And again, I think this is an excellent problem. We just weren't ready for part of it. We just hadn't covered that other part yet. 1769 newtons. When her normal weight is around 700 newtons. So she's pulling an incredible amount of G's. Well, I got all excited. I forgot to see what the problem actually asked for. What does it ask for? Find the speed. Okay, so we found it. Oh, this is 15.6. Okay, I've got to change all my variables and our kilograms. I was looking at the answer solution. Oh, Jesus. Okay, so I was using 16.6 and 60 instead of these. So let's go ahead and plug these back in real quick. So I know that, well, I just know that this is equal to the square root of 2 times 9.8 times 15.6. That's going to be my speed. 17.49, correct answer. Okay, so what's the centripetal acceleration? I'm going to take that 17.49 and square it. I was looking at mine instead of this one. Squared. Divided by, oops. Divided by 15.6. Submit. That's correct. I'm starting to learn now. 19.61. How many times her weight is the normal force? So we take the normal force, which in this case let's go back here. So for the new calculation, the normal force would be this. Whoop, sorry. Let me go back real quick. 59. And what was her, what did I calculate the centrifugal acceleration to be? 1961. Twice. It's 3 times. Let's just go with 3. You saw me do it, so you take the normal force, you find out how to get the normal force, and then we just do 3. Correct answer. I think most of y'all are going to be 3, right? Because I was using 16.6 and 60, and this is 15.6 and 59. They still give me the correct answer, so we're good. That's a long one, so we'll go on to the next one. We'll